Example of a free fall problem. A stop rocket shoots straight up, goes all the way up, and all the way down. Straight up. Keywords, straight up. Now, what's wrong with this picture? That's right, we don't draw things that shoot straight up. If we really did shoot it straight up, you'd be nasty little antisocial terrorists shooting rockets out of Gaza, trying to blow up informants, and it would go straight up, it would go straight down, it would blow you up. There's a video of this on YouTube. Can your boo? Talk it out, brothers, not with rockets. Nobody ever draws this straight up. And when we draw this on a graph, the graph we're drawing is not a y versus x. It's a y versus t. This axis doesn't tell you how far forward the rocket lands. If you're doing a pure free fall problem in one dimension, it is going straight up, it is going straight down, it lands where it started. This is not the significant dimension here. If you're doing a 2D projectile problem, you will notice that the horizontal and the vertical are completely independent. You do one problem in the horizontal direction and one problem with the vertical direction. Fall means we're only working in the vertical direction. If someone tells you that the distance from here to there is 5 feet, what's wrong with that statement? This is physics class, good old US of A here at Zell High School. What is wrong with saying that the distance from here to here is 5 feet? First, this is not distance, this is a graph, this is time. It's measured in seconds. The distance from now to 1:30 p.m. is not 5 feet. Second, this is physics class. You can't use 5 feet for anything. If you wanted the distance from here to there, usually called something useful like d or possibly y, that would be in meters, not in feet. All right, start the problem by listing what you have. If the rocket has left the launcher, you know the acceleration. It's negative 9.81 meters per second squared. Choose your axis so that the positive is up. Now, if you're here, you know that d equals 0. That is a complicated equation. You have to check that you're in the vertical direction, check that this is vertical, check that you know this, check that this is vertical, check that you know that. I don't like that squared. You can do the problem located over here, but you can also do the problem located over here. And if you choose this as the halfway point for your problem, you can cut the problem in half like this. If you're interested in the initial velocity of the rocket, you'll need some extra information. From here to here, this is the initial point in your problem. This is the final point in your problem, because you're doing the problem only as far as the upward trip. You know the velocity at this point. The velocity at that point is 0. Do you know the time? Well, if you have a nice symmetric parabola, then you can see on the graph that what goes up must come down. The time it takes to go all the way up should be equal to the time it takes to go all the way down on the other side. So if your time is 5 seconds from ground launch to ground landing, how many seconds would it be up here at the top? If it took 3 seconds from ground launch to ground landing, how many seconds would it be at the top? You can pick an equation with VI, VF, A, and T, and you can solve. Having done that, you can also, if you're looking for the change in displacement, you can pick a question with VF that you know, and T. Note you have to change the sign on the acceleration. And see where that brings you in one step without needing VI. If what you want to know is the downward journey from here to there, well, you will get the exact same answer with a slightly different list. Acceleration is gravity. You are still in free fall on the way down. It's quite recognizable. Well, the time is the time it took you to start the problem at the top of the peak and go all the way down. What goes up must come down. As before, there's your total time of 3 seconds. In this case, you started the problem at the top, and if you want to find the final velocity, algebra, or if you look at the slopes on either side of a perfectly symmetrical parabola, logic will give you the answer. And hey, yes indeed, you can still use that same equation we planned to start with. You know the initial velocity, you know the time, and you know the acceleration. Note that this sign is negative to get you how far down you're going to fall. Keywords down and fall. What should the sign be, positive or negative, if you're starting here and falling down?